For the rest of this video series on linear optimization, we use the sensitivity sheet to perform a variety of what-if analysis on the model, moving beyond just a single, unique optimal solution. The questions confronting management are those of the uncertainty among model parameters. What if one or more of them change? What would be the impact on the optimal solution and the course of action it would imply? Some of these questions can be answered with the sensitivity report, but we must be cautious with the interpretation because they pertain only to the impact of changing one parameter at a time, leaving all the rest at their base values. Then, if we want to examine the impact of another parameter, we have to assume that the first one we analyzed before is also at its base level. We start with the decision variables x1 and x2 and the allowable increase and decrease ranges for the corresponding objective coefficients C1 and C2. If we change one of the objective coefficients while holding the other one and everything else in the model constant, the objective function will change, of course, because it changed the coefficient, but the optimal solution, specifically 1.2, 2.4, we've seen a million times by now, will stay the same. Okay, so for example, if we either drop drug 1 profit from $2 to 1.5, okay, or increase it by $2 to 4, okay, of course the profitable change, but the optimal solution 1.2, 2.4 will stay the same. Same thing here. If we decrease the drug 2 marginal profit, which is currently at $3, by $1.50 to 1.50, or we increase it by $1 to 4, the same effect will take place, which is that the profit will change, but the optimal solution 1.2, 2.4 will stay the same. Where are these numbers coming from? Okay, where are these numbers coming from is the sensitivity report right here, this highlighted section. Okay, so the objective coefficient for drug 1, right, the marginal profit on drug 1 of $2 can be increased by 2 to 4, or can be decreased by 50 cents, right, from 2 to $1.50, as shown on the slide here, right? If you do that, of course, the profit will change, but the optimal solution will stay the same. Okay? By the same token, again, you have to imagine that the objective coefficient for drug 1 is back at its base level of 2, and now you're dealing with drug 2 objective coefficient. If you increase that one by $1 to 4, which is the maximum allowable increase, okay, or if you decrease it by $1.50 from 3 to 1.5, again getting the same range as for drug 1, of course the profit will change, but the optimal solution will stay the same. So to quickly show some of this, go back to the premium solver, zero out the optimal solution, and then make these changes, some of these changes one at a time. I will just do a couple of increases on drug 2, for example. Okay, so drug 2, based on sensitivity report, all right, I can increase it by $1 at most, right? So first I'll increase it by 50 cents, which is mid-range, to 3.50. Right here. I'm going to run the solver real quick to show you that, of course, the optimal solution is higher because the marginal profit per drug 2 is higher, but the optimal solution is the same. So profit's higher, optimal solution is the same. If I increase it to the max of the allowable range, which is 4, okay, and zero out this guy, you will see that the optimal solution changes, but it's only because now we are back at that alternative optimal solution case, right? If you look at the alternative optima, this is exactly what we had. We change the drug 2 marginal profit from $3 to $4, okay? But as we know from previous video, right, the 1.2, 2.4 is also the alternative optimal solution for that same example. So let's put this back to 3 so it's the same as it was before, and switch back to the presentation. Okay, next, all right, we're going to discuss the concept of a reduced cost, which is a little tricky at the beginning. Okay, reduced cost is, as the definition states at the bottom of the current slide, okay, the amount by which an objective function coefficient, C1 or C2, needs to be reduced for non-negative decision variable that is 0 in the optimal solution to become positive. Yeah, so that sounds a little abstract, granted to you. For our case, for the base case, if you go to the sensitivity report, the reduced costs for both are 0 because both values of the optimal solution for drug 1 and drug 2 are not 0. They're both strictly positive at 1.2 and 2.4. So to understand the concept of the reduced cost, we're going to switch to non-binding constraint sheet, which has the chart also copy pasted here on this slide, and we'll notice that the drug 2 marginal profit was further increased to 5. Right here, non-binding constraint sheet further increased to 5. Okay, so looking at the chart either here or on the slide, okay, you can see that the profit contour lines have significantly changed their tilt upward again, right? Like you're lifting them up by the right side here, like that. Okay, from the original ones that had relatively pronounced slope to the ones that are more flat or shallow, as this slide shows, right? This is because having a larger coefficient next to x2, right? This guy here, this is the one next to x2, all right, makes the slope a smaller number, right, and therefore shallower in the profit contour or profit line equations. Okay, so why this long detour to profit line discussions? Because with the shallower tilt, the higher profit is going to come from the vertex 0, 3 rather than the optimal vertex 1.2, 2.4. And you can see that on the previous slide, right? Because of this tilt. Now, as you're moving these contours up, the last point that they will touch in the feasible region, right, bounded by material and labor constraint, is going to be 0, 3. Is going to be 0, 3. Okay, so the new optimal solution is now the 0, 3 vertex, which basically states that it's not optimal to produce drug 1 at all. So drug 1 is at the 0 value. Labor constraint is going to, as you'll see, is non-binding with 9 hours, with that slack of 3 hours we've seen several times before. So again, to see that, all right, just make sure that your x1 and x2 are zeroed out, and then simply run the model, and you'll see it quickly converges to 0.3 with the optimal profit of $15 because, again, of the higher marginal cost here, right? And you can see that the material is binding, right, and the labor has $3 in slack. And when you do that, I'm going to have to do it one more time. We need to because I forgot, we need to pick at least the sensitivity. We don't really care about the answer report. So you're going to get these sheets, answer report 2, sensitivity report 2. I'm going to move them after the binding constraint, and I'm going to zoom in to the sensitivity report 2. Okay, specifically, we're going to be looking at the reduced cost on X1, and drug 1 is now not a 0. It's a non-zero number. It's negative 0.5. Okay, so basically what that says is that the profit margin, which is currently $2 for the drug 1, must be reduced by negative 0.5, which is a double negative sentence, which means actually that it has to be increased by 50 cents to at least $2.50 to make it profitable to produce drug 1. Okay, and that is coming right from here, this number. Okay, so what we're going to do, we're going to switch to the reduced cost sheet, and the chart that's again copy pasted to the presentation. Reduced cost sheet, zoom in a little bit, change the C1 from 2 to 2.5. Notice that C2 is at 5. Okay, and then when you run it, you're still going to get 0.03. So the drug 1 still has a 0 production. Okay, the optimal solution is $15 as it was before, but notice that now 1.2 is again an optimal solution. It's an alternative optimum in this case, not a unique one, but it is an optimal solution because if I type 1.2, 2.4, I will get the same 15 bucks. Okay, now to make it unique optimal solution, right, after zeroing this out, you're going to have to increase you're going to have to basically increase the marginal profit slightly more above 2.5. Like if you do 2.6 and run it, you'll see that 1.2, 2.5, 2.4 rather is again optimal solution. If you increase it to 3, which is my last one, 0, run it, you'll get what I have, I believe, on this slide. On this slide, right, which is showing again the unique optimal solution as 1.2, 2.5, and that optimal profit contour of $15.60, just like here. Okay, and this is a good place to pause.